Hello everyone, I'm Isaac Ajao. I welcome you to this month's edition of Ekiti R Users Group training. We had uh, a training last in July, in June or July. It was on fundamentals of analysis using R. Today we are going to regression and ANOVA in base R, analysis of variance in base R. I have these subtopics: simple linear regression, and that is when we have one predictor and one outcome. Multiple linear regression, when we have several predictors and one outcome. One-way ANOVA, this is when we compare means across 3 or more groups. Two-way ANOVA, when we study two factors and their interactions. So simple linear regression now. The concept is we model relationship between a dependent variable y and one predictor x, and this is the model. The beta naught we see here is the intercept. The beta 1 is the coefficient of regression, or regression coefficient of x, and this is the error term. These are the assumptions underlying the use of the regression. The first one is linearity, normality of residual. The second one, the third one is constant variance. We call it homoscedasticity. When we have several variances, we say heteroscedasticity, and that's going to be violation of assumption. So example is predicting exam score from study hour. Multiple linear regression. This is relationship between outcome y and two or more predictors. Don't forget, the one I mentioned before now is simple linear regression, where we are predicting one outcome from one predictor, but multiple, where we have many predictors, two or more predictors, predicting one outcome. So here, still using the example of exam scores and study hours. So we are increasing the predictors here. Exam score depend on study hour and sleep hours. Though in real life it may not be like this. It's not everyone that study, for several hours and that's going to make it in exam. But we are talking about, and this is just an example. In real life situation, it may be and it may not be. Say sleep hours, a student that sleeps too much may not have good exam score. Now look at the assumptions here. The only one, they are just the same, but the only one I added here is multicollinearity. Collinearity is when you have a significant relationship among your predictors. It's not expected. So there should be no collinearity. That's one of the assumptions. Then one-way ANOVA. We are comparing means of 3 or more groups based on a single factor. Here, the YIJ I have here is the response variable. This is the grand total. And here we have the treatment, and there we have the error term. The assumption are the independent groups. The group must be independent. The groups we refer to as the factors. And the response, the value for the response, the residual must normally be distributed. Then we should have equal variance, just like we had here, equal variances. And that's a homoscedasticity. Then example, compare exam scores across departments. Here we have the department here, the computer science, biosciences, engineering, they are example of the department. So, and what makes this one different from linear regression? The difference here is that, in regression, we are having our exam scores as continuous data. And the independent variable are also continuous. But in this case, the factors are not continuous. That's why they are called factors. They are categorical. You can see, you can only depict all this development by values or by code. You can give 1 to CS, 2 to bioscience, and 3 to engineering. So when you want to compare means across groups, and then the groups are now represented by values or by letters. One method we use to analyze such data is what you call ANOVA. And what makes it one way? When you are having only one factor determining your response. Though the factor may have many levels, like this one factor department having how many? CS, bioscience, engineering. So when we have two factors, we are going to two-way ANOVA. So this one examine effect of two categorical factors plus their interaction on Y. Look at this. The first factor is alpha. Second factor is beta, and combine them together is interaction effect. So assumption are the same thing of one way. Then example, impact of department, you see 3 level, and gender 2 level, male and female on exam scores. So this two-way ANOVA. Don't forget, one way is when you have two factors determining your response. Two ways when you have two factors determining your response. Then this is just a quick recap of what I've just said. Simple regression is one predictor. Multiple regression is many predictors. One way ANOVA is one factor, 3 or more groups. Then two group is t-test. That's why I put it here. Don't confuse the two. We use one way ANOVA for one factor or 3 or more groups. When you have two groups, just like this here now. Assuming I have two groups here, exam score this one way ANOVA. If the department just has two groups, I will not go and use a one way ANOVA. I will use t-test. So one way ANOVA, 3 groups, 3 or more groups. Then if it's just 2 groups, then you use t-test. Then two-way ANOVA is 2-factor possible interaction. So the next thing you're going to do now is to have it done on RStudio. So hands-on. So you can come out, you can on your system. I have my code here I'm going to use. As I'm going to be explaining, you can do it along with me. So this is where I'm going to download our resources. If I click this now, you're going to see this PDF. To download the sample data set, as I already populated them, but after the training, I'm going to show you how we are going to download all the materials we are using in this training. Then to download R itself, come here, this is crownrproject.org, download RStudio. The IDE I'm using, that's the integrated development environment I'm using, is RStudio. I'm downloaded here. Then to join our community on Telegram, just click here, you will see it take you there. Then to join our meetup page, because we organize training periodically, you can join us here, so you can stay updated for many other things we do in our training. So I want to go to the hands-on aspect now. Thank you. So you're welcome. This is where I have my code for the analysis. Don't forget, it is regression and ANOVA. So this is, I've written, though we need a data set to do this, and data set is here. You can see simple linear regression in one. I have 4 sheets here in this workbook. I have simple linear regression data. I have multiple linear regression data. As you can see, x1, x2, only one y. I also have one-way ANOVA here, and I have a two-way ANOVA. You can see one-way ANOVA having just one factor. I call it group. Two-way, you can see factor 1, factor 2, see response. So I just prefer using one workbook. Each of these data sets can actually become one file, one Excel file. I just prefer this method. Even if I have 20 data sets, can be representing, can be in just one book, one Excel book, workbook. So all that I need to do is just name them like this. So these are sheets. I have more, but I don't need it. And delete this. So these are the data sets I'm going to use. Okay. So this is the training data set. The name of that data set I show you is training data set .xlsx. Maybe I should explain this first before I go into it. Excel has various versions. The version I'm using, I have my Microsoft for Office is having the version is 2019. I use Office 2019. If somebody is using anyone lower, it may not be. You are not. You won't have XLX. It's going to be XLS without this X. So and if you are using lower version, having this file extension, having SLS, not this. I mean this. If it's just XLS, you don't need this library. You don't need this library. You just import it, it's going to answer you. So this is how to import your data. The library here must be installed. What are the libraries? Libraries are a set of functions or algorithm you have written to perform some task. Library. It's not only R that uses library. Python also uses library. You import and you install it. How do we install our libraries? Okay, let me quickly show you. There are several ways. As when I want to install this read Excel. What read Excel does is to read file extension of this type. Now, just say you want to install now, example, you say in, that is install dot packages. It has given you option. You can see I suggested for you. So let me input read Excel. Read is to import data. You want to import data that is in Excel format, and that format must be known is XLSX. I've said it. If it's CSV, you don't need it. But since I'm using a recent version, that's why I need it. So and I'm using this method because I have all my files inside the workbook. So, and you can see what I put here, and I've commented it. I put hash and I write some things here. Any text you see after hash sign like this, they are referred to as comments. So this is a comment here. It's just to tell us, I put this there to tell us, to show to those learning participants the next task I want to perform. File path, the data is in my working directory. What is working directory? This is my working directory. A directory is just a folder where you keep everything you need, where you keep your data, where you keep your script, where you keep your image, because you want to use them, your charts, which you have imported from somewhere. So that's your directory. It's not only app that uses directory, even starter uses directory, working directory. So your working directory, let me quickly show us my own working directory. This is KTR users. KTR user. Okay. My own working directory is somewhere. Yes. This is my working directory. KTR user. Dedicated for this training. See everything I have here. All these things are the one revealed under here. See, this is my working directory. So you must create a directory, otherwise you will land, you will see that it will waste your time because you'll be using paths. So instead of using paths, you only need to keep all your documents, everything you need inside that particular directory. And see all of the things I have. This is the training that I opened the other time. You can see all of these things, they are here. So let me go back. Make sure you create a directory. And directory can be on the desktop, can be anywhere. Just make sure you know where it is. So you're going to launch your script, whatever you want to do, right from that directory. Yes. Now, I call this file, say training underscore dataset. Must be the same name you have given it. You want to call in your data. So for simple linear regression now, is the first data here. Is the first sheet. So I want to bring it out because I want to use it. So I now say the SLR you see here is the simple linear regression underscore data. You can give it anything you want, but I prefer giving any name I'm going to assign to my data, something that I will always remember. SLR. Some people use their name. If I put Isaac here now, how many Isaac will I have? But SLR means simple linear regression. When I get to multiple linear, I will say MLR, multiple linear regression. When I get to ANOVA, I will, all those average. So it's good you assign a name that you will always remember. So it's a good habit. Now look at this read underscore Excel. This read underscore Excel is the function from read Excel. Read Excel, you see. So I was about showing to us how to install library. You can see I've already put it here. Install the packages, then read Excel. Then also make sure you are connected with internet access. So when you enter this now, it will install it. Though it won't waste time before it finishes because I already have it. Wow, now that's one way. You can also come here, just come to the menu here. Come to the menu here. And see, come to menu, come to tools. You see install packages. And see it has done it here. Package read Excel successfully unpacked and MD5 subject. Downloaded binary packages are in this place. You can see. So this is another way of installing. You can just type the name of the library you want to install. You can see it's there. If I click on install, it will install it. So those are the few. Then you want to install directly from RGUI, graphical user interface. Just type it the way I put it here. Then, so as we have done that, so now the first thing to do here, we have brought the data. And you want to print. Now you need to run the line. That is to print the data. Click on run. Or you just say Control Enter. Two ways. If you want to run any script like that, just select it and press Control Enter. You could not read it. Why? Because we have not run the library. Run the library first. Library will open doors for other function. When you don't run the library, R will not understand what they're talking about. So since I've run it like that now, I will run this also, that my file is this. I will now run the read Excel. The main function here that's going to read your data to R is this. And you have to be very careful. The simple linear regression you see here must be the same name you have on your data. Don't put lowercase and go and use uppercase on R. you have to be very careful. You run this, you can see anytime you are running line of code like that and R is just moving to the next prompt, not giving you error message in this orange color, it means you are doing the right thing. Or if you do the wrong thing, you are going to see, you can see where we made error. You can see error in read exec, could not read this. So it has executed it. But we have not seen the data. You can say print the data. You can see I've already assigned SLR underscore data to it. So when I want to print this now, I just do it this way. Then you click run. You can see it has brought the data. You can see 3.8.3 to 2.9. Let's check. You can see 3.32. It has approximated it 3.8.32 to 2.9. Can you see? So it has given it to us. So you can see. Now we have 40 more rows. If you want to see the first 6, just put 8 here. 8. Run. You can see the first 6 rows. If you want to see the last 6, will be tail. Run it, you can see this is the last 6. So okay, now having done all of this, can now move on to fit our model. Now I didn't do something, but it's there. This is summary statistics. You can do a summary statistics before you fit your model. I prefer doing my summary statistics before, but no problem. I have 2 variables there, so I can do summary statistics for this x and y. So let me do summary statistics. I want to summarize that. I want to see the mean, the median, the minimum, the maximum before I go to data fit, model fit. So let me say summary. Summary is the function for you to summarize your data. This summary. Okay, can you see? So here, can you see now? This is minimum. The minimum we have here in this data. Minimum we have for x, minimum we have for y, and the maximum, and their mean. You can see for mean for x we have 4.1. First quartile, that's 25th percentile. Median is 50th percentile. This is 9.7. The mean is 10.10, 10.10. Third quartile, which is 75th percentile. Then the maximum. You can see the same thing for y. We have x and y for simple linear regression. You can go ahead. So this is summarized. This summary of the data. Summary of data x and y. So it's good. It's always very good to do that before you even go to fitting of the model. So now let's now fit the model. So this is SLR. SLR is simple linear model. So LM you see here, LM is linear model. This is the function we use to do our regression. So we want to regress your y on x. Y is the dependent variable and x is independent variable. Some people call response variable input variable. Outcome variable. While x is input variable. It ranges from one discipline to another. If you are talking among people in econometrics, you call this one regressor. Regressor is your x and your y is your predictor. So now you need to instruct R where to get the data. You now say data is equal to SLR underscore data, which is this. You can see data, you must instruct R where to get data. So this is the data. Run this now to feed the model. So I've told you it has fitted it. You can't see the result until you ask. So to now see the summary of the result, say summary, the summary of this model, it will give it to us. But if you don't want to go to summary, it will give us a very brief result, telling us, showing us the model. And that can be gotten by just copy that and run it here. It will give you all this. So now look at the data. See the result here. See the result. And this model, look at it. This summary of the result of what you mean, 6.323. This is the intercept. This is 1.942. So to write out this model is very easy. Just say y equals 6.32 plus 1.942x, which is the same thing as what I showed you to us when we are doing simple linear regression. You can see y b0 plus b1x plus error. You can see the same thing here. So these are y is equal to 6.32. These are beta naught. This beta 1. This x. Okay. Now we can move on. Now we can have a detailed result. Detailed result will show us the contribution and other statistics, especially the p-value. You also see the r square. You also see the adjusted r square. You can make this one does not have p-value. You can't take any decision here. So that's why we normally use summary to summarize the results. Run. Can you see? See the results. You can see this one is not scanty as this. This one is detailed. So residual now. See the residual. I think you remember the residual. Residual is you can't get residual if you have not fitted your model. Residual is the leftover, the deviation from your when you remove your predicted from your actual. The leftover is what you call residual, and it is the one we even look for when we are saying we are testing for normality. The residual, the values here must be normally distributed. So the residual minimum there is minus 12. The one Q here I have to use first quartile. That is 1/4. That's 25th percentile. This is the mean there. This is 75th percentile, and this is the maximum. Now, the one that is most important to us here is to look at this. You can see this result, coefficient. See the intercept. 6.32. Just like the way we get it here. You can see. X 1.94. Just like the way we got it here. Now, look at standard error. See the t value. And this is the p value. The most important here, well, let me say two of them are very, very important here. The estimates. The estimates are the contribution here, contribution of your intercept, contribution of your x to your y. So this 1.9. And look at now, I said p value is also very, very important. If it's the one that help you to take a decision whether you are going to reject H naught or you not reject it. What does the H naught say? H naught tells you that there is no relationship. That's beta naught is equal to 0. Here, beta naught is not equal to 0. We have values for beta naught. Then this one tells us more about it. When do we reject your H naught? You reject H naught when your p value is less or equal to your alpha. What is alpha? Alpha is level of significance. Most of the time we use 0.05. That's 5%. So in this case, look at it. Now, R has one important advantage over others. And this is the issue of the stars. You can see it shows the significance. How significant? This 0.01 is less than 0.05. Is significant. But 8.99 e raised to power minus 11 is more significant, far more significant than this. This 0.00000, you can see. So you can see 3 star telling you that X is highly significant. So now it's a very good relationship. It has a relationship. Now look at the other ones. We have multiple R square and we have adjusted R square. We have F statistics, we have the degree of freedom, we have p value. You can see the p value here is the same thing as this. So generally we can see the model is significant. Now what do we say about this R square? Either I use the adjusted or use the multiple R square. The two of them they are always very, very close. Now we can say this model can explain 58.6 or approximately 58.7 variation in the response variable. Let me say it again. This model explains 58.7 variations in the response variable. Is it not a good model? Anything above 0.5 is okay. So we can now move on. So with this, if I want to report this in my paper, there's a way I'm going to write it. So now we are not through yet. We now go to scatter plot with regression line. You see, some people even prefer, after summary statistics, they go to scatter plots. Scatter plot, just as the name depicts, you want to visualize the relationship. Visualize the relationship. What does the relationship look like? Even before modeling, you can visualize it. That's your y against your x. Response against predictor. Dependent against independent. Look at the way R does it. If I want to plot this in Excel, it's very simple. I will just highlight and run scatter. It will give it to me. Line plot will give it to me. But in R, this is the way we do it. Let me explain this to us. You can see SLR underscore data, $x, SLR underscore data, $y. Let me not talk about all of this for now. These are just decorations, telling you why. But the one that is really doing the work here is this. Now, R sees the first variable you put here as the one that will go to x-axis. Unlike starter, if it's starter you are dealing with, the first one you write here is going to be your y. But in starter, in R, this is how we do it. X will come. Then why am I not writing just ordinary x here? Why am I adding $* and putting the parent name of the data here? Because R will not see x, because x is not just an entity standing alone. X is under the data called SLR data. See, look at it. The SLR data. So you can only see, x and y are inside, but you can't see them outside. So you can't just refer to x and y. You see, they are like how would I put it now? Parents, when you know somebody, you don't know their children. For you to have access to the children, you have to have access to the parents first, because the children are inside the room. So for you to have access to the children, you have to get access to the parents first. And that's what I'm using here. So there's a way I can do it that I will not make use of this. But let me run this for it. So now let me explain the remaining one. You can see SLR $x. What I'm doing here is to isolate x. SLR underscore data y, $$ is to isolate y. Go to SLR and bring x. That's what we are instructing R to do. So the name you see here, that's the name on top of the chart you want to plot. Anywhere you see name, you can see it in different color. Then let it be in quotes. Then X lab, this is X label. Label are referred to as the names of the axis. So for X axis, call it X. For Y axis, call it Y. So now AB line, you can see I want it. Let me explain what AB line means. AB line is the line of best fit. The line will pass through. It normally passes through your scatter plot. Then you'll be able to say something about the relationship. So I want the color to be blue. If I want it to be yellow or red, I see red. So I can use number if I know the equivalent, the number equivalent to this particular color. For example, now if I want to know the colors, I come here, colors. R has over 600 colors. Yes. And see, so many colors. This is 655, 656, 657 colors. can see yellow green, can see white smoke, can see tomato too, turquoise. Eh? You can just look at, well, for those of us that are that do not know any other more than the primary colors, the red, blue, black, so but it has a lot of, that's why R is very, very good when it comes to data analysis, data science. Now, I want to test for, okay, let me run this. Let me run this. I want to run this without the AB line for you to see what we refer to as scatter plots. You can see scatter plot. Let me zoom it here for you to see scatter plots. This scatter, you can see Y and X. Y and X here, this one shows that, it's showing the relationship between your Y and X, and the relationship is linear. And as Y is increasing, X is also increasing. So this is positive relationship. Though line of best fit you pass through this place, some point are far away. That's why the relationship here cannot be too high. It can't be up to 0.7. I've not tested it. It can because of this line. Well, let's check. We can have already scatter plot has given you clue of the kind of relationship we have. You can see it's not zero, but it's not bad. You can see, and it's positive. Let me close it. So I want to now put the AB line here. You can see you cannot plot AB line. AB line is line of best fit. In fact, what it does, when you design your model, you have predicted, you have actual, you have residual. What we plot that AB line is the predicted. That's why it's always very straight. Let me run it. Run that. You can see the blue line on it. I see it now. So and I see. So this is the line, and the point here. Now the further the point away from the line, the worse the worse your model. So the lines, you should capture at least very very many points so that you have a good prediction. Okay, now the next thing is to test for normality. There are various ways we check that. Use QQ norm, we have PP norm, we have histogram, we have Shapiro whiskey test. So these are because when your data is not normally distributed, you have violated one of the rules, and one of the rules I mentioned, is it linearity, normality of residual constant. So it must be normally distributed. It must be linear. So now look at it. Shapiro whiskey is one of the tests we carry out, and it must be carried out on the residuals. I'm not even showing you the residual. Let me run the residual itself before I run the Shapiro whiskey test residuals. And I've explained what residuals are. Your actual minus your predicted, or vice versa. Whatever thing you have on ground is residual. Run this. You can see. These are values of residuals. And how do we get? Can we get it? Now you just remove your actual from your PDF. You have not even shown us predicted. Okay, we can get predicted. The value. To get the predicted, let's see. What's our model? These are model. Our model is this. So how do we get the predicted from it? Predicted. Just predict model. Okay. So predict that. See. So this is predicted. These are the predicted values. How do we now get? Okay, let me do this manually for us to see. Okay, let me now see. All right, residual. The residual will be, assuming I don't know that it has a function. Residual itself is a function which you can use directly to obtain, but assuming I don't know it, I will now say residual is equal to a the actual the actual data is y minus, so minus predicted value of predicted. So here's the model. Go and see the one I put here. So yes. So what about the residual now? Residual. So these are the value of residual. So I want to have a table that will show the actual, the residual, and that will show the actual, the predicted, and the residual. It's possible. I will now use what we call data frame. Data frame is to aggregate your data on a table. To put or arrange your data on the table, they must have the same dimension. Now, I want to have now let me call this table actual, predicted, residual. Then see what I type to get this. Just press Alt and minus, give you this. Now, data frame is a function, dot frame, that will give you your table. So data frame, I say I need, we say okay, the actual data, that's my y, is equal to the data. Yes, I don't want this to appear in my result, so I want actual to be there, comma. I will now use predict. That's for prediction. I say I need actual, predicted, and residual on the same table. I will say okay, predicted, or this one like that. Then the remaining one is residual. Residual will now be residual will now be equal to actual minus spread. I'll define as spread here. Let me now run it. Actual not found. Okay, because I'm just assigning it, no problem. It's going to be okay. All right. I use, so the predicted will be, just predict this. All right. So let me run this. Can see, let me just look at it. Yes, that's accepted it. So to now see the table run, can see this is actual, predicted, residual. Very easy. If I want to write everything together, now what I did here is it is step by step. I didn't jump any step. I did this not using any function. I did it just like normal mathematics. Actual are the values. And you can see the reason why I like this table, because it reveals the nakedness of the model. See, look at it. Actual, this is the value And these are the values on the original data. See, C 22.9 and 23.47. Same thing, C 23.47 up till the last one, which is 50. The predicted value are the one predicted by your model. This is why you know whether your model is good or not. The beauty of a model is for it to be able to predict something close to the actual or the original values. See, we have 22.9 and it's predicting 22.4. You can see, look at the residual. Residual is removing this from this. You can see these are the leftovers. So look at it. The value of the residual must not be, the highest we have here is minus 12. When we have actual as 12 and the model is predicting 24, all other ones are not too much. See, 0, minus 2, 28, 30. I see, I've done it manually and I've gotten the result. So the one that you see, this line of best fit, the value used to plot it is this predicted. Let's see. So I want to continue because of time. Right. No, let's now test for normality. Shapiro. So we are going to use residual for that. Test it. So this is it. How do you know this is normally distributed? Though? Let me explain the reason why I said it's normally distributed. Because look at Shapiro whiskey normality test. Data is residual, this. Now what you want to use here is p-value 0.9648. Now the secret here is that for you to know whether your data is normally distributed or not, you will not reject each knot. Because each knot here says that the data is normally distributed. Unlike other hypothesis statements we make for regression ANOVA anywhere, when it comes to test for normality, test for homoscedasticity, all those kind of tests, you do not reject each knot for you to have a viable result. So this one must be greater than 0.05. And because it's greater, you do not reject each knot. And each knot says data is normally distributed. So do not want to reject it. So here, this is normally distributed. Right? Okay, let's move. So we have used Shapiro whiskey test to test for normality and sparsity. And you want to check, data science, data analytics, people want to see visualization, they want to see charts. Even when you are presenting to PhD level, they want to see your charts. It's not just saying you reject each knot. Though this is more scientific, we have done, but we still need visualization. So there's one we call KQ norm. KQ norm will give us, we are still using residual for all of them. You don't go and be very careful, don't use the actual data, you use their residual. That's why you don't check for normality before you design your model. You must have fitted your model before you say you can check for normality, because the residual. How will you get residual without the model? So that's why we are doing it last. So now let me say something. If this one fail the normality test, what do we do? I will talk more about this later. We always have way out. So visual check. KQ norm. See what the way I put it. I just put this. This is a very simple code. Just put residual inside. That's all. KQ norm, KQ line. This one will be plotted. The line will put line across it. The histogram, just east. Just once you type your east for histogram, it will give it to us. Then the main you see, as I said every time, is to give it a particular name. So run it. I want light blue. That's why I put light blue there. You can see. You can see it here. So this is dome shape. Now, how do you know that your data is normally distributed here? It is symmetrical. This is symmetrical. Dome shape, bell shape. If it is skewed to the right or to the left, that is not normally distributed. So let's go to multiple regression. I won't spend more time here because they are almost the same thing. The only difference is that you can't plot your scatter plot You can't have your scatter plot using multiple regression unless you want to be doing it one after the other. So the way we arrange simple linear regression data, the same way I'm going to bring multiple linear regression data. Don't forget is the second sheet here, x1, x2, y2. So x1 and x2 are the determinants of our y2. y2 is a response variable while x1 and x2 are independent variable. So now what I plot here, you can see. Though I've said it, I'm going to say it again. Make sure you write it exactly word for word the way it is on your Excel, because it can be frustrating if you want to bring your data to R and it's not coming and you are seeing so many error messages after you do it well from the beginning. So you want to fit the model, just run this first. So after you have run it, it has accepted it. Now feed the model. Just now let me explain something here. You can see y2. This approximation shine is normal. It's at the top left hand side of your keyboard on your laptop. Same thing we use when we are dealing with simple linear regression. I forgot to say it. You can see anywhere you see it, you are saying you are regressing y on x. You are regressing y2 on x1 and x2 because we are having multiple regression. If they are more than 2, you can have x2, x3, x, and you can see, you just put plus there. Then the data is ML and data. That's all. Then you summarize your data. Your model, just the way we did it the other time. So as I summarize my data here, the other time I can also summarize it here. So here, the summary of the model, run it. So the summary of the model here, so we have summarized it. And x1 is 1.4, its contribution of x1 here is 1.4, contribution of x2 is 2.4, and they are all significant. The two of them are significant. And look at the R square. The R square here, 0. This is a little bit higher than that of, meaning that this model is better. Why? Because the R square has increased. So meaning that the R square, another name for it is goodness of fit, or coefficient of goodness of fit, coefficient of determination. Coefficient of determination. We want to, because it's one of the statistics we use to say something about the fit, which is the model. And generally you can see this 2.68 telling us that is highly significant. So this 0.7355 shows that 73.6 approximately of the variation in the response variable is explained by the model. This is very good. Telling us that whatever prediction you are making here is reliable. It's reliable. So now let's move and see to test for. Let's now look at the diagnostic plots. So this is why we diagnose our model. We want to see certain charts to tell us more about it. So here you see plot MLR. Remember, so you can't do scatter plot here because we have x1, x2. If it's just s1, scatter plot will work. But here it can't work because it's more than 1. So we run it. So this is what we normally have. We call it diagnostic. Okay, here it has plotted it. See, residual versus fitted residual. You can see KQ residual. Now what do we say about this? Now look at all of this. You can see the residual scattered everywhere. And standardized residual and theoretical quantiles. We have scale, location, and fitted values, then the leverage, and the standardized residual. Now let me explain this. The residual and the fitted, one of the assumptions is that they must be scattered everywhere. They should not follow a particular pattern. Now here, for KQ, this value you see here must not be too far away from this line. Some of them, but they are not too far. They are not too far. It's talking about normality. Now how do we run that to show that more? Okay, let me explain the reason why I put MF row C to this matrix. I want to have a 2 by 2 matrix. If I don't put this one here, if I don't put this one here, if I comment this, meaning that I will not run it, if I just want plot MLR model, these 4 charts will come out one after the other, making it 4. And see, to see next plot, it. See, I see all of them coming up one after the other. You see. So to save space, that's why we are using that. So that's return. So let me return it. If it's like 6 plots, I can have 3 by 2. That is 6 rows, 2 columns. So 3 by 2 will give us 3 rows, 2 columns. That means 6 plots. So now I return it to 1 because I want it back. So that's why I put it there. So the Shapiro test. Now, don't forget Shapiro test we use for normality when we are dealing with simple linear. The same thing we are going to do here. So let's see the results. Oh, the result is amazing. Shapiro Whiskey normality test. Look at the p-value 0.009 is not normally distributed. This is not normally distributed. So because you are rejecting each not here. So let's check. Let's check what we get at that time. See, the reason why you can see these points are far away. Some of them are even far away from the line. That's why it's not normally distributed. So think you can now look at the one-way ANOVA now. Let's check one-way ANOVA. Now, when do we use ANOVA? I told you when I was using the slide. One-way ANOVA, what it's dealing with is to compare means across a categorical group. We are comparing mean of a particular entity, maybe blood group of some people, using a particular, maybe the same house or the same school or department. So, but it must be one factor. So one-way ANOVA data, this is it. That's it. This one-way ANOVA, this data. So group A, how many of them? I told you the minimum of 3. If it's just 2, use the test. So we have 3 groups, and these are their scores. So we want to compare. Now the aim here is to test whether the mean of scores across the 3 groups are equal. mu1 equal to mu2 equal to mu3. That's H naught, which is the null hypothesis. Okay, you want to reject it. So now what we are going to do, you can see ANOVA 1. Really, we have read this just the way I've been reading the other ones. Bring the data. Now this library is very important. Agricole is what we use for Duncan multiple range. What do we use it for? It's not part of what I presented at that time. We use it if you find out if your result shows that the difference, there's significant difference among the groups, meaning that the groups are not equal. So where exactly is the difference? Is it in the first group or the third or the second? So what you are going to use is what you call Duncan multiple. Though there's one called Turkey. Turkey is mostly used by people in Greek, but Duncan is mostly used by people in Biosciences. It depends on the one. That's why I put it to here. So it's going to give you the same results. I mean different results, but the same interpretation. Now the first thing to do is to feed the ANOVA model. So instead of using LM, you use AOV. Run this first. So AOV is analysis of variance. You can see the way I put it. You know, I say I like assigning variable name that has to do with what I'm working on. This ANOVA 1 model. I use 1 because I have 2-way ANOVA. So this one carries 1. Look at the way I put it. The scores here is dependent variable. Group is independent. We don't use dependent and independent in ANOVA. We use response and factor. So you can see scores. See the score? Score. Then group. So same thing you see here. See, so when we are talking about this, what we mean is that we want to find out whether the mean of these scores are the same across the groups. So I've told you that time you try and instruct R where to bring the data. So the data is ANOVA 1 data, as you can see it here from Excel. Now summary of the model. Now run this model. When you run it, it has done it. Now for you to see the detail, just like we did in a regression, run the summary. Now let me show you the detail of the summary. Now you can see. Now if you are familiar with ANOVA, this is what you call ANOVA table. Now group, you know we have three. We have three groups. We have A, B, C. A, B, C. So now degree of freedom will be your number of degree of freedom minus 1. This is it. So and this is the residual. Now look at it. Look at this. This sum of square, this is mean square, this F value, this is probability value, this is P value. What is important here is this P value. You can see it has 3 stars, and I've told you all the time, this shows how significant, this is highly significant, telling you that the difference is highly significant. There is significant difference in the scores across the 3 groups. So they are not the same. They are rejecting each other, say they are equal. So where exactly are the differences? That's what Duncan or Turkey, we call it post-hoc test. Post-hoc, I think I wrote it somewhere here. Yes, one way ANOVA plus post-hoc test. We need it. So we have done that, but before that, we want to know want to plot. You know, I said this time we are now is not just doing significance. You have to show it. Visualization is very important. So let's plot the group means. You know, let me show it to you. The means of each of these. If you add all of these scores together, all the A's, divide by the number, it's going to give you the mean for this group. So it's the mean of each group we are comparing. I want to show it on a box plot. Why are we using box plot? Because we are dealing with continuous data and categorical data. This course is a continuous data. The group is categorical. This is continuous, this one is categorical. So to show such on a chart, you cannot use bar chart. Bar charts deal with count data, but this continuous. So this one will not just show you information, but you will also see some things like distribution of the data. So you can see box plots. You don't need to install anything before you use box plots. You don't need to buy there. That's why I'm using base R. These are things that have come with R. So scores, group, then data you instruct R where the data will come from. Then the name, one way or another. X label is group. Then you can see these are just to show you to add to your chart. Then the color I put light blue there, I can put red, just like blue. So run it. When you run it, the result is here. See, this is one way ANOVA. This is one way ANOVA. See. So from this, we can quickly see the group that has the highest score. Group C. Group C has the highest score. That's around, I think, like 62. And let me quickly explain this. You see, these are whiskers. The top, the down. This is the minimum. This is the maximum. What you see at the center here should be the median. And you can see, now, you can see one point out here. This one point here is outlier. There's a value in that C that that is higher than all of the values there. It's outside here. Let's go there. C. Can see. Okay. This is 50. I think this is 53. Yes. 53 is ridiculously low. Can't be in the group. So 53. Can see. 53 is, and that's why it's outside. So talk about extreme value, talk about outlier. This one will show it to you. This is what's called box plot. Very powerful. We use it in our data analysis. So the post-hoc test, just as the way we did for the other one, we're also doing it here. Now Turkey. We want to do for Turkey. So Turkey, run it. We want to see where the significant difference is. Is it in A or B or C? Run. See the results. So here, now, look at the group. Group B minus group A. The difference is this. Where do we get this difference? You don't need to worry yourself. It's the mean. The mean of B and the mean of A. You know, I told you, you can easily get the mean. Just add this. The mean is here. Add B, the mean is here. You have three means. So it's the mean that you are subtracting here. B minus A, the difference. C minus A, the difference. C minus B, this is the difference. Now look at the p-value. These are the lower and the upper cases. Now look at the p-values. All of them except the last one. So the difference is significant in the first two. This is the last one that is not significant. So we can conclude by saying that the difference is in B and A. Your difference is here. So you don't just say I reject it not. Okay, where exactly are the differences? So this one has shown it. We call it post-hoc. But mind you, you don't need to go for a post-hoc test when you do not reject it not. I've seen a lot of people doing that. You don't need it. Even to PhD level. You see people saying, I've done my post-hoc. You don't just do it anyhow. You don't need it. Now, post-hoc test for Duncan. Unexpected symbol in post-hoc. Okay, let me run it again. Run. Yes. See the results. So complex. What we need here is not everything we need. Those that's giving all detail. These are their scores. You know, Turkey did not reveal the mean, but Duncan has revealed. The mean for A is the 50.19. If you are a doubting Thomas, you can go and use calculator and get it to you. You get the same thing. The mean for A is 50.19. Mean for B is 55.99. Mean for C is 61.10. These are the standard deviation, these errors and all of them. Now look at it. This Q1, Q2, Q3. This alpha 0.05, degree of error range. This is detail. Now look at their scores, 61. This is group AB. Now what do you listen to this? That's why I say people in biosciences normally use Duncan. They like it. Means with the same letter are no significant difference. Can you see? Now look at it here. 61, 55. They are, look at it. This one shows that they are not the same. They are not the same because they have different letters, and the rule is that the mean with the same letter are not significant. So if I have A here and I have A here, it means they are not different. So since they have different letters, it means all of them are different. So that is it. So you can see their papers, they will write small a, small b. So now let's test for normality using Shapiro test and the QQ norm. This one is also we look at it, you can see p-value is 0.06 if it's greater than 0.05. So meaning that this is normally distributed. We do not reject it not. And if you look at the QQ plot, the normal QQ plot, you can see the values are not far away from the line. They are not far away from the line. So the last one here is two-way ANOVA. Two-way ANOVA, where you have two factors. So the first thing to do, just like we have been doing it, bring the data in. Then you run it. Now, then before I move away from this, the response, the factor, now I put a star here because we are dealing with. Now, in two analysis of variance, if you remember, I put it there that a comparison of the first one, the second one, and the interaction. That was make it two-way. You can combine two factors together. You can see this is it. This is the first factor, this is the second factor, then the effect of the combination of the two. You can see that's what makes it better at times. You can combine the effect of department and gender. What is the impact of these two on exam score of students? We have some other ones that are complex than this. You can have 3, you can have 4. So now to run it, the same code, the only difference that you are putting star here. Then the data will come from ANOVA 2. You can now summarize this data. When you summarize this, it's giving you these results. Now, interesting, look at factor 1 is significant, highly significant. Factor 2, we call them main effect. Main effect. The effect of the first factor is significant, second factor is, But when you come to look at how R is writing interaction, factor 1 together with factor 2. So p-value is 0.77, meaning that it's not significant. So interaction is only the main effect that have significant that are significant, but we don't have interaction effects on this model. So because this is 0.77, so here now interaction plots. You see, all of them have their. Don't forget, for simple linear regression, we are using just scatter plots. When we come to ANOVA, we use box plot. But for two-way, we are talking about interaction plots, where they cross one another. We want to see what is happening. So to plot that, I've told you the reason why I use $sign. If I don't want to use that, I have to write here data is equal to I put ANOVA 2 there. But since I'm not using that, I have to use $sign to bring up the data, because data is here. You can see it's factor 1, factor 2 under training data set, which I've given another name here. So that's why I'm using $sign to bring them to list them here. So I want this, I want this, I want this. So the 3 variables are the one I brought out here. So you want to plot them. You want to plot factor 1 together with factor 2 together with response. So that's what I'm doing here. And because we are going to have 2, so you have 2 colors, red and blue. So run it. See. So these ones are staying apart. They do not cross one another. You can see. It's supposed to cross. Since they are staying, apart, no relationship. They are not contributing. So that's why you see that one 0.77. So you now test for Toki, just the way I've been doing it, post-hoc test. Okay, before we even, now we need it because the model is significant. That's why we are going for Toki, and then we go for Normality Test. So here you can see. Now low, no, high, no. These are the differences. Now you can see the differences are in the first one, the second one. So it's only one that is not significant. That's 0.16. All other ones are significant. These are things that will make your paper robust and acceptable when you do what's supposed to do. Not just say I reject each of them. Then when you reject, we are. So it means even in this interaction, it means we don't need interaction effect here. So these are things we have shown to us. So normality test for this, just the way I've been doing it, no different. The only thing is that you just make sure that the model you use last, you are going to put here, you must use residuals. So let me run it. So this is, I established the fact that it is significant. So the normality is shown to us here that is significant. So we are going to see here. So this is it. The values are not too far away. That is it. We have come to the end of the training. If you have any question, you can get across to us. Even through Meetup, if you send a message, you're going to receive it. And let me go back to where you can actually meet us. See, this is our community. If you click on this, take you to our Telegram. You can see we have 55 subscribers. Ekiti, our user group. So it's already here. You can see. If you click on that, so you can join. So if you have not joined, that's why it will take me to that place. Then you also join our user group, Ekiti our user group. When you click on that, it takes you here. You can see you can join this group if you have not joined. These are the trainings. We did this one in June 21st at 12 p.m. Getting started with R, a powerful tool for data analysis and research. So many, we still have so many to do. So the next training, by the grace of God, I will talk about what you can do if there is a issue with our data. It's not normally distributed or it's violating some assumptions. What can we do? So all those things will be taken care of. Can we use Python on RStudio? Can we use R on VS Code? People are asking so many questions. So just follow us. If you have any comment, let us know. So thank you very much. So I will make sure the video is ready as soon as possible. Thanks so much. Goodbye. Thanks for watching and listening.